right, I'm going to give you some time with this page. What a definite integral does is it takes on an interval. It creates an infinite number of those little rectangles that we've been drawing. It draws way more than we could ever draw. And so what happens is when you squish infinite number of rectangles into that area, the width of the rectangle becomes so tiny that basically it can go all the way up to the curve. There's really no wasted space between the rectangle and the curve, getting us to the actual area under the curve. So that's what you're seeing happening in an integral. It is a different notation. At the very end of today, we'll talk about another way that this can be shown, and that is using summation notation, because it's summing up an infinite number of rectangles. So the things that you'll see here that we will want to make sure that we understand, this is the symbol for an integral. It's a definite integral when we have numbers on either end of those. Those are the interval in which we are taking our integral from A to B. The function follows that, whatever that function is. If it's more than one thing, we usually group it in a parentheses, followed by our variable of integration, usually as an x. We'll eventually see some other variables there as well. So follow your function with dx. So we would read this, our integral of f from A to B. Give you a second to get that information down, and then we'll move on. Typically, it's what variable your function is written in terms of. But sometimes we'll have some mixed ones in there, which we'll talk about later as we get into integration techniques. Right, I was going to say similar to when we did like our related rates type of stuff, where we take it with respect to time instead of respect to x. All right. So there are ways to do this without a calculator. There are ways to do this geometrically. And again, it's just finding the area under the curve on whatever interval they ask us to look at. This would be a common question that we could do absolutely without a calculator, and that is the integral from -2 to 2 of the square root of 4 minus x squared dx. First of all, to help us out a little bit, we would start by graphing the function, and our function being y equals square root of 4 minus x squared. In this format, it's not as obvious what shape we are looking at. If I were to kind of manipulate this equation a little bit, I could square both sides, right? Put my x and y on the same side by adding x squared over. And are you recognizing the shape when I write it like this? What are we looking at? A circle, right? Now, I'm going to take a second and undo what I just did, because as you're solving this, algebraically, I really should have a plus or minus here, right? So when we are looking at this as it has been solved for y, really if the positive there is there, which is what we're looking at over here, that is the top of the half of the circle. And if it's the negative in front of it, that would be the bottom half of a circle. Okay, so we have the positive, so we're looking at the top half of a circle, not a full circle. Other things to talk about, let's go back to the circle equation that we were familiar with when it says x squared plus y squared. Our transformations would happen in there. But what's the 4? Close. Radius squared. Okay, so if that's our radius squared, that will help us get to the radius, right? Which means our radius is 2. So we're drawing the top half of a circle that has a radius of 2. And then we're going to find the area under that from -2 to 2. So if I were to draw a picture of what's going on, we've got this circle here, radius of 2, just the top half. We are integrating from -2 to 2, which happens to be the ends of my drawing there. Usually will be. And that's the area I'm trying to find. Well, I can go back to my geometry days and remember the formula for the area of a circle is pi r squared. But we're only doing the top half of it, so I'm going to put that 1/2 in there as well. Our radius is 2. 1/2 times pi times 2 squared, or 4, is 2 pi. So one of the ways, again, we can evaluate, especially non-calculator-wise, is by identifying the shape being created and then just using the area formula for that shape. Questions? Units squared, area, units squared. All right. What if the function inside of our integral is a constant? We do have a formula up here for how to evaluate that integral. It says that we would do the constant times the difference between the ends of our interval, b minus a. I don't necessarily have to remember that formula. We can still attack this geometrically. So while you guys are kind of getting that jotted down, I'll show you what this would have looked like geometrically. If I have a function that is a constant, f of x equals 2, y equals 2. Remember, when it isn't just a constant, in our picture, that would look like just a horizontal line at whatever that constant is, some c value. And if we're asked to integrate that to find the area between that and our x-axis on some interval from a to b, as I connect those up to my constant, it's creating for us what kind of a shape? A rectangle, right? And the area of our rectangle is the base times the height. Well, the base can be found by finding the difference between the ends of our integral. B minus a, so there's the base, times the height is going to be whatever that constant is. So it's not that you have to memorize some random formula. You can do that geometrically as well. Draw in the function, horizontal line. Draw in the ends of your integral, makes a rectangle, base times height. Okay. Using that idea, again, very basic, but we can use an integral to represent this situation. We kind of did one like this a couple days ago. It says a train moves along on a track at a steady 75 miles per hour, so its velocity is 75 miles per hour, from 7 a.m. to 9 a.m. Express the total distance as an integral. So in our integral, we will say when we start and when we stop, 7 to 9. And then we would put in our function for our velocity, 75 miles per hour. And I'm actually going to call this dt because our expression is in terms of time, right? Miles per hour. If I use the formula above, we would be talking our constant times the difference in our integral, 9 minus 7, which would be 7 times 2, or 150 miles per hour times hours would be 150 miles. Again, kind of a picture of what's going on here. That's that constant of 75 up here. Evaluating from 7 a.m. to 9 a.m. gives us that rectangle. Questions? Okay. I'm not going to change the situation. We've still got a train traveling at 75 miles per hour. But what if I were to, instead of asking you from 7 a.m. to 9 a.m., I asked you to find out how far it travels from 7 a.m. to 2 p.m. Okay? I want you to talk with your table partners about how could we still express that as an integral and come up with the total distance traveled from 7 to 2. If I were to just blindly follow the pattern that we did on the last one, and I went to set up my integral, it's when we started, 7 a.m. to when we stopped, 2 p.m., right, of our function, 75 miles per hour. What problem do we run into on this? The 2, right? The 2 is the issue, because if I were to follow the formula that it tells me, it would be taking 75 times 2 minus 7, or 75 times negative 5, so we traveled a negative distance when we traveled longer, okay? So what fix did you guys come up with? Military time, you got it. 2 p.m. is what time military? 1,400 hours, all right. That's the fix. If we flip from like morning to afternoon or whatever, we have to pay attention to, we can't use that 12-hour clock, right? We've got to flip into like the 24-hour clock to actually represent the number of hours that have passed. Any questions on that? All right. One of the things that can be confusing is that when we are talking the fact that an integral is the area under the curve, or the area between the curve and the x-axis, area is not a negative concept, but integrals can be negative, okay? So that can be confusing for people, kind of like distance is never negative, right? Area is not negative, but we will get negative answers. So how does that happen? Well, negative, when we are talking integrals, indicates that our function is below the x-axis. So it's not that it's a negative area, it's that the area that we have is occurring below our x-axis. Yes? No, it will not. And I think tomorrow we're going to start looking into where some of it is above and some of it is below, and how do we deal with that. Nope, that's the big part of why we use this, is because it can help us with things like total distance, with things that go above and below our x-axis. But kind of breaking it down, just sticking above or below right now. What you see on this first one, again, if we were to, again, blindly follow the formula that we had, this is a constant. So I know I can find this integral by taking that constant times the difference in my interval, 8 minus 4. Negative 15 times 4 would give me an area, an integral, of negative 60. We don't have negative 60 area. It's telling me that our object has an area of 60, but it's all falling below my x-axis. If I were to, again, kind of help us out visually here, negative 15 is going to be some function down here, right? If we're down here at negative 15, integrating that from 4 to 8, we again see that it's going to be that rectangle, and that rectangle, the area between that and the x-axis is below our x-axis, negative 60 degrees. Questions? Okay. The next one is not trying to trick you, but just to show you that just because we are finding the area in a negative section of our x-axis, asking you to do the integral of pi over 4 from negative 5 to negative 1, does not automatically make our area negative. Pi over 4, again, is just a constant, right? I know pi looks like our variable, but it is just a number. So pi over 4 is a constant, and we're supposed to be finding the area between that and our x-axis from -5 to -1. If I were again to follow my pattern that says I'm supposed to take pi over 4 times the difference, well, -1 minus -5 ends up being -1 plus 5, or 4, times pi over 4 is pi. Okay, and again, a picture of what's going on here. Although it's happening way over here, there's your pi over 4 function, -1, -5. Again, it's just giving us that rectangle. Any questions? Area under the curve. Okay, so we saw a circle at the beginning. We've seen some constants which are creating rectangles for us. But just like we saw before, they're not all going to be just rectangles. So finding other shapes that we know how to find the area of geometrically. So something like this. The integral from 1/3 to 4/3 of -3x minus 1 dx. How do we attack something like this? Again, you could totally do this without a calculator. Draw the function and highlight for yourself where we are totaling up the area and identify the shape. And then we will do our area formula. So I would start by graphing this one. Now I'm supposed to be going from 1/3 to 4/3. That kind of helps me with figuring out where I want to draw the function. 1/3 up to 4/3, we don't really need to go that far. Like 1 and 2. Okay. Start at 0, go up to 2 maybe. This at 0 would be down at -1, right? And we've got a slope of -3, so down 3 over 1, down 1, 2, 3 over 1. It's going to be a picture something like that. That's our function. And I'm supposed to be finding the area between that and our x-axis from 1/3, and 1/3 would be approximately right here, to 4/3, which would be approximately right there, right? And kind of highlighting that for myself and saying, okay, well, what shape am I looking at? This we've seen already this week. What shape is that? A trapezoid, okay? And we talked about, yes, there are multiple ways of finding the area of a trapezoid. You can break it into different shapes like a rectangle and a triangle, or we can remember the area formula for a trapezoid, 1/2 times our height times base 1 plus base 2, just being cautious that when we say height, we mean the distance between the bases. And when we say base 1 and base 2, it's our parallel lines, right? How long are our parallel lines? Now, when I'm finding an area formula, I would be doing positive lengths here. The distance, what is the distance between our bases? 1. From 1/3 up to 4/3 is a distance of 1, right? And then our bases, remember, come from plugging that into our function. Now, when I plug this into my function, I do get a negative length, which normally we're not supposed to have a negative length. And I'm going to talk about 2 different ways you could attack this. So if I plug 1/3 in here, -3 times 1/3 would be -1. -1 would be -2. So this point right here is 1/3 comma -2, which means this base has a length of 2. So as I'm doing my area formula, you notice I'm making it positive. Same thing if I plug 4/3 in here. 4/3 times -3 is -4. -1 would be -5, which means this base has a length of 5. So our area is 1/2 times 7, 7/2. But our integral that's below our x-axis. Anything below our x-axis is negative area, so -7/2. Questions? All right, this one should look familiar, so I'm going to let you and your table partner work on this one, please. We'll talk about it in just a second. What shape are we looking at? Circle. Top half or bottom half? Top, right? Because it's positive radical. If we put a negative in front of it, we'd be looking at the bottom half of it. Radius of what? How is this one different than the one we did earlier, though? It's only a quarter of the circle because of the interval they're asking us to find this on. It's only from -5 up to 0. Here's -5, here's 0, which means we are stopping finding area there. Well, when I compare that to a full circle, that is only 1/4 of a full circle. So I take our circle area times 1/4, or divided by 4. Our radius is 5. 5 squared is 25 times pi times 1/4. 25 pi over 4. Questions on that? All right. The last thing I want to look at is this. We are not spending any time because it's really not necessary, but the basis behind integrals finding the area under our curve is that it did what we were doing the last couple days. It's creating rectangles, and it's making those rectangles so skinny that it's filling in the area accurately. Well, that is a summation. Do you guys recognize this symbol? Summation of infinite number of rectangles. We don't need to know how to write this, and it's very distracting with all of that's in there. What we do want to do is be able to see this and understand where and what that means about the integral that it's actually happening. Okay, so let's talk about how to do this. First of all, this part all right here is, again, kind of distracting. That's your integral symbol. Summation kind of gets turned into this long S here. Okay. What follows is going to be your function, but the way these are created, the function is going to look super weird because it's going to have like some C sub k, M sub k, this weird looking variable here. Well, every place that that is, this little thing right here, we will go through and replace it with the letter x to create the function f of x. And then the last part is this. Delta x and dx are just two different ways of saying the change in x. So we can use the mathematical symbol delta. When we move to our integral, it will say dx. Now the interval on which we are doing that does not show up anywhere in this summation notation. That is something that would have to be told to us separately. So it either will stay a and b or move to whatever integral they happen to give us. This, if you were to go to your book, is the way that it explains or describes the situation, and look how confusing this is. Each m sub k is chosen from the kth subinterval of a regular partition of the indicated interval of n subintervals of length x. You guys all got that? Good? Yeah? Okay, moving on. Express the limit as a definite integral. Okay, don't stress over that paragraph. I get that that is very confusing, but they're saying that they're creating rectangles of regular partition, so equally spaced rectangles. Okay, and then we are of n subintervals, so they're n, meaning that n is heading towards infinity, or that we are creating the partition so that it's basically going to nothing between that and your curve. If they then say, okay, this is the summation notation, take that and convert it to the integral notation. That's a big old way of saying write this like that. Okay, so let's do that. This is our crazy, fancy, overwhelming way to write that same information in interval notation. Draw your interval symbol. They will tell us what interval we are doing this on, and it's over here, from 0 to 3. That's your A and B. Start at 0, end at 3. Then they give us the function in here, and that's the next place we're going to look. Well, this is my f of x right here. After I convert m sub k's, all the subs, to x. Okay, so it's 3x squared minus 2x plus 5. That's all I write here for my function. And then again, change the delta x to dx. Done. Questions? You won't see that often, but we do need to see it enough times that you could recognize how to jump to this. We will spend the rest of this semester on your integrals in that notation. Okay. Questions? All right, your assignment, page 286, doing 1 through 21.